Okay, so, ooh, wrong problem. Okay, here's the problem. So we got a integral, right? And we see that it's going to be integrated over a triangular region. And it's a single line integral. Well, it says to use Green's theorem, so we're going to go from a single line integral to a double integral. So I'll state Green's theorem. It's basically f dot dr, and you're saying that this is the same thing as the integral p dx plus q dy, and Green's theorem now says that that is the same thing. Okay, so if you're integrating a single integral, you're going over some curve, a closed curve, right? Because this is closed. And then you're going to transform that into a double integral over a domain, and it's going to be q with respect to x minus p with respect to y dA. So this is Green's theorem. Okay. Now, if we see right here that this would be p and this would be q, so p is equal to 1 plus x cubed, q is equal to 2xy, right? Because p and q follow the order. Okay, very important to follow this order. Now, if we take p with respect to x, what do we get? I mean, if we take p with respect to y, well, we get 0. But then if we take q with respect to x, what do we get? We get 2y. So our integrand reduces down to this. It's going to be 2y dA. Now we ask ourselves, what is d? Well, d, okay, well, if I draw out what d is, it's this triangle that goes from 0, 0 to 1, 0 to 1, 3, and then back. So I'll draw the orientation. And we can see that this is what? What type of orientation? This is counterclockwise. Okay, so we can use this version of Green's theorem. If it was clockwise, you just times this by -1. But since it's counterclockwise, we call counterclockwise positive. Okay, nonetheless, let's move on with this. So we can describe D as this region that is in x and y. Then we can describe its x being from 0 to 1, right? And then we can describe its y being from 0 to some function y equals mx plus b. Okay, so we ask ourselves, what's the slope here? And then we can see that it's just going to be, so if we think about this, right, what's the change in slope is change in y divided by the change in x. The change in y is 3. The change in x is 1. And then it starts at 0, so plus b, it's just plus 0. Okay, so these are our bounds. We're going to use this stuff for our bounds. Okay, so now if I set up my actual proper integral, it's going to be from 1 to 0, and then from 3x to 0, it's going to be 2y dy dx. And as you can see, if I integrate with respect to y first, as it says so to do here, and you should integrate with respect to y first because that's the only way you're going to get a finite value. If this was switched, you wouldn't get a finite value. So in general, right, the integral that comes first must be the one with the variable bounds. Okay, so what I'm going to do is I'm going to do the first integral, but I'm going to do it on the inside in the parentheses. So the first integral is going to be the dy integral. So if we integrate this with respect to y, right, it's going to be y squared. And then we have to plug in 3x and 0. Okay, so now if we do this again, but plug in the bounds. So 3x squared is 3 squared and x squared times each other. So it's going to be 9x squared. Okay, dx. Now if we take this integral, what are we going to get? We're going to get, it's going to be x cubed. 3x cubed, right? From 1 to 0. Right, you raise this to the power 3, and then you divide by 3, that's how. And then you'd see that this is just going to be 3. So your final answer is just 3. There you go, it's nice.